Today's speaker is Ryuichiro Kitano from KEK. He obtained his PhD from Tsukuba and then did several postdocs in the US. And since 2009, he's back in Japan. And since 2013, he is at KEK, a faculty member there, and also at Sokendai University. And he will be telling us about 3D dualities and how to go from 3D dualities to hadron physics. So.
Thank you. Thank you for introduction. So yeah, hi everybody. I'm gonna talk about this formally looking, title, but it's not quite formal thing. It's a hadron physics. I'm basically working on phenomenology, so I think it's not too theoretical. I hope. And this talk is based on the collaboration with the Yokokura-san, Kan-san, and Shimon Yankirovitz. And also there's a work in progress with my postdoc, Matsudo-san. And I'm gonna talk a little bit about that. Okay. So you can see the cursor, right? Maybe, yes.
Yes,
okay.
Yes.
Thank you. So, okay, let's start. So I'm kind of somehow interested in the theta term in QCD for these several years somehow, and the theta term, as you know, is a very interesting term and some peculiar term in QCD. This is the renormalizable operator FF dual, and the theta is kind of an angle which parameterizes the vacuum.
Then let's just pause it first, right? Okay. Because after we resubmit,
maybe I can continue. And this FF dual term has a property that if you integrate over space-time like this, you get an integer number, and theta is a parameter associated with it. And if you integrate over this operator, you get the integer. That's something, very surprising for a graduate student, and probably, I couldn't believe that this, FF to the integrate over, you get the integer, but this is actually true. You can prove that easily. And so this term is actually a total derivative. This is topological because it's an integer number. So if you take a derivative with respect to the gauge field, you get 0, of course, because it is integer. So that means it doesn't appear in the equation of motion. So at the classical level, it's nothing. But somehow, at the quantum field theory, theta plays an important role even in the vacuum of the theory and the spectrum of the theory. Okay, so my talk is pretty much related to this theta angle, and that's it. And there are many mysteries associated with theta parameters. First of all, the very first question would be this: is theta physical? And this is okay. So the low level answer is that okay, it doesn't appear in the equation of motion. It doesn't look like it's physical. But at the quantum level, as I said, it is physical if the up quark is massive, or one of the all the quark mass is non-zero, non-vanishing. Then theta is physical. That you can prove. And of course, as you know, it's very interesting that this theta angle is known to be very small. It must be very small to be consistent with the experimental constraint, neutron EDM. So why small? That's the famous strong CP problem. And that's a very important question in the standard model. And that may be a hint to the physics beyond the standard model, and could be related to the dark matter physics and so on, through axion, for example. And also another type of question is that what happens at theta equal to pi? That's a very interesting question, actually. And theta equal to pi, if there are quarks, it's almost nothing. It corresponds to the quark mass changing the sign. Quark mass m to minus m is equivalent to theta equal to pi. So that if there are quarks, it's not so interesting. Well, it's actually interesting if quark mass, if you change the quark mass. But anyway, so what happens to theta equal to pi is particularly interesting in the limit where quark is all massive, in the Yang-Mills limit. And the people kind of understood what happens. And at least in the large N theory, SUN with large N, 3, 4, 5, maybe 4, maybe 3, okay. People think that the spontaneous CP violation happens. That means that, okay, at theta equal to pi, there's a symmetry to flip theta to minus theta, because pi to minus pi, and minus pi is the same as pi by adding 2 pi. It's angle. So there's a CP symmetry at theta equal to pi, and that will be spontaneously broken at the vacuum. That means FF dual operator gets a wave in the vacuum. That's totally different from the usual theta equal to 0 vacuum. There are degenerate vacua, and there's a spontaneous violation of CP symmetry. And that is probably happening okay, that is known to be happening at large N. And even at finite N, there are many evidence that, not evidence, there's actually proof that if confinement persists, then spontaneous CP violation must happen. So that we kind of think that the SU3, for example, confinement is maintained. Well, of course, nobody knows actually at theta equal to pi, but anyway, if confinement persists, then the CP violation should happen. That kind of argument kind of recently appeared through the anomaly matching condition of the one-form symmetry. And also another type of question is that what happens at high temperature? So people use the instanton calculus to understand the theta physics. For example, the axion potential at high temperature is calculated by using the dilute instanton gas approximation that everybody use for the calculation of the misalignment mechanism for the dark matter abundance. That's the usual way to calculate. But is it really true if you include quarks, and especially when quark is very light, as in our universe? Is theta still, theta dependence still controlled by the instantons, or more quantitatively, how high temperature is necessary for the instanton calculus to be trustable? So that kind of question is very interesting. And some people say that, okay, at high temperature, there may be no physics, no theta dependence in phase. That kind of argument actually still there. So it's the open question, actually, what happened at high temperatures. So it has a very big impact in axion physics. And also the theta dependence in SU2 gauge theory, that is also interesting. As I said, SU3 is probably a category of large N. People believe that. Oh, of course, nobody knows, but people believe that. But SU2 may be in the category of small n. That means it may be totally different from SU3 theory. And as I said, we can prove that, related to the theta equal to pi question, we can prove that if confinement persists, then CP violation happens. But in SU2 theory, there's a possibility that CP actually violation doesn't happen, but confinement is broken. That means a deconfinement phase appears at theta equal to pi. So that kind of unknown question, unknown, open question there. There are many open questions associated with theta angle. So that's why I'm kind of interested in this thing. And could be related to the physics beyond the standard model. So it's a very interesting topic. And I've been working on actually with lattice QCD friends about this kind of problem. And there are many numbers of papers I published, but I'm not going to explain all of them. But for example, this is the lattice calculation of the temperature dependence of the axion mass, for example. You can calculate. And even I can calculate at up to very high temperature. And it seems that dilute instant on gas picture is pretty good, even at very low temperature, like critical temperature. But this is without quarks. If you include quarks, there are many, controversial calculations, and no question is not settled yet. Okay,
so
this
calculations are pure Yang-Mills.
Yeah, Yang-Mills theory. So those two are Yang-Mills calculation. So it's not so interesting, but still we can see that the instant on picture is pretty good, even at low temperature. So that you can see in a totally non-perturbative calculus. Yeah. Also, we can see this is the SU2 theory, and okay, this is kind of completely different things, but it's a 2-point function of FF2, the operator, and that you can see that the instant on picture and the lattice pretty much consistent at high temperature, but at low temperature it's different. So that you will see the different picture in at high temperature regime and low temperature regime, and kind of thing. So I'm not going to explain all of them, but this is there are many interesting businesses going on associated with data. So today, the topic I'm going to present is that some exotic possibilities of hadron property in QCD based on the consideration of theta term. I say exotic, that means really exotic. and we are going to compactify one of the space dimensions. So let's say Z direction is compactified on S1. So it's not our world, but still it's going to be interesting discussion. So yeah. So anyway, I'm going to compactify one of the dimension and discuss the large radius and small radius limit. So large radius limit is kind of our QCD, our world. But I actually put non-trivial theta background. I'm going to explain what it is data, but anyway, it's a kind of axiom background. The theta term is winding around this S1 direction. I'm going to explain later. And by doing this exercise, I'm hoping that this consideration gives us some new qualitative picture of hadron world. That's our goal. And why I'm doing this is that actually there are many discussion and many progress in the three-dimensional gauge theory. So that's why I was interested in this business. So low energy limit of this background is of course three-dimensional theories because low energy limit, we are compactified one dimensions. So if you go below the compactification radius scale, we are in a three-dimensional world. So low energy limit is three-dimensional theories. And as I said, it is motivated by the recent discussion on three-dimensional QCD, where there are various dualities are proposed, so that we can use at least guided, can be guided by the knowledge of the three-dimensional QCD. So this is the thing. So I'm not going to present many equations. It's a full of stories like this. You can ask any question at any point. Yeah. Okay. And let me introduce one of the progress in the three-dimensional QCD. So it's a few years ago, Komaragowski and Seiberg actually wrote a phase diagram of QCD3. And I'm going to explain this diagram later, but basically, based on the duality, they propose that the phase, okay, so this horizontal line is the fermion mass. As a function of the fermion mass in QCD, there are various phases appears, and they proposed this kind of phase diagram. One limit is topological field theory, another limit is another topological field theory, and in between we have some nonlinear sigma model. So this is the picture. But anyway, so this kind of analysis is motivated by duality and supported by duality in QCD. So that will be very interesting. Okay, so let me explain what is QCD3. It's a very fundamental thing. Okay, so of course it's a SUN theory coupled to fermions as in the usual QCD4. But what's interesting is that there's a one parameter called K, the Chern-Simons level K. This is additional parameter in the theory. So the Chern-Simons term is like this. It's you know, you cannot write down this kind of term in the even dimension. In odd dimension, we can write down this kind of term. It doesn't look like KG invariant, but it is if this K is integer. So the KG invariance requires this K parameter to be an integer. So that this integer gives you another parameter in the Lagrangian. So that is labeled like this, SUN K theory. So we have this term. So that's it. So QCD, and usually, you know, Maxwell term and fermion kinetic term, and this Chern-Simons term. That's the QCD theory. And in a component, it's like this. So anyway, bunch of, the most important thing is this AF coupling. So what's nice in 3 dimension is that the Maxwell term, the gauge coupling has dimension, positive dimension. That means Maxwell term, we have gauge coupling in a denominator. So the kinetic term is irrelevant. So the low energy physics is dominated by this Chern-Simons term. This K is integer, that means, you know, dimensionless. So this is actually a topological term. There's no metric associated with it. So the this term is the most important term at low energy. And so this determines the low energy physics. And what's nice about this term is that, okay, if you take derivative with respect to A naught, that gives you a charge, right? So that, you know, A naught coupled to rho, so it gives a charge. So this, if there's this Chern-Simons term, A naught coupled to F12, right? F12. F12 is a magnetic charge, magnetic flux. So that means the charge becomes magnetic charge. So the Gauss law constraint, which should be satisfied in any physical system, is given by this. The charge, if you have a charge, there must be associated magnetic flux. So if there's a charge here, the magnetic charge is also associated with it. So this is a somewhat different picture for something extraordinary in 3 dimensions. We have charge, magnetic charge is associated with it. So what happens is that, for example, electron, if we have Chern-Simons term, we have also magnetic charge. Then the electron goes around the electron. Usually, you get the, you know, fermion phase -1. But because we have a magnetic charge, we have a Aharonov-Bohm phase on top of that. So the statistics is screwed in 3 dimensions. If you go around the particle and same, you know, particle and particle exchange, usually what you get is usually fermion -1 and boson +1. That's the usual case. But in 3 dimensions, if you exchange particle, you get some different phase. So the fermion boson, that kind of thing becomes meaningless in 3 dimensions. So this is kind of a peculiar feature of QCD in 3 dimensions. But anyway, that's the thing. So based on this, you know.
Can I ask you this clarifying question? You're working in a Euclidean 3D or 2+1?
Yeah, 2+1.
Okay.
So that in a time slice, it's just a sheet.
Right. Okay. Okay.
Right. And on the sheet, you can exchange the particle, but you get some fancy phase coming from this Chern-Simons term. Thank you for the question. And so the boson fermion doesn't matter. So the so based on this, not based on, but so there are famous, you know, even going to this before QCD, there are there are many known dualities in 3 dimensions. For example, free fermion is probably dual to U1 gauge boson, U1 with one scalar field. So, you know, it looks totally different theory, but it's known to be the same theory. So that kind of thing happens because if you say fermion, but the statistics is boson, so that it's screwed. So that kind of thing happens.
So simply saying the spin group is abelian there, right? It's just a rotation, U1 or something, and that's you don't have a kind of quantization of spin or something. Is that correct?
I
can think about that
way. I don't know how Lorentz group works. Yeah, maybe, yeah, just one, maybe, yeah. That's right. Well, I'm not sure actually, but anyway, yeah. But anyway, so it's true that the 3-dimensional fermion bosons are kind of different from the usual 4-dimensional intuition. Okay, so there are conjecture duality, non-trivial dualities are proposed by Haroni. There are many people, but Haroni actually summarized and listed the precise dualities. Still conjectures, but anyway. So the second line is the most important for us. So the UN gauge theory with level K with NF scalar fields. So this is a definition. It gives you a definition of theory. It's actually the same as this theory. Well, same meaning the low energy duality. So low energy physics is the same. SUK, you know, this level K becomes this inside, you know, the rank of the gauge group. Rank, not rank, it's you know, SUK. And the level is like given by this funny combination and NF fermions. So it's kind of amazing to me that this completely different 2 kinds of theory looks it's proposed to be the same at low energy, and this is even without supersymmetry, so non-supersymmetric with finite n. So this is gives you a nice duality picture. The conjecture meaning that it's a conjecture, but still passes lots of non-trivial checks so that people can believe that this is actually giving the same theory. And this is heavily based on the level rank duality in Chern-Simon theory. This is mathematically just true that if there's no scalar field or fermion field, this is just true that the SUNK theory is the same as UK minus N theory. So this is, you know, if there's no matter field, this is completely just a topological field theory. So the observables are just Wilson line and linking numbers, those kind of topological thing. And it is known that those 2 theories are just the same. And this level rank duality plays an important role to show that this duality is consistent. So to me, that's very interesting. Totally different theory, and even fermion theory and scalar theory give you the same physics. And I'd like to discuss the possibility that this duality is something related to the KEK hadron duality in 4 dimensions. So it's a kind of radical, but okay, this side gives you QCD, right? So if there's something describe the same physics, this must be a hadron, right? So the KEK hadron duality may be the relation of these things. So that's the thing I want to discuss. There may be a similar 4D picture that is motivated by the 3D duality. So for that, I'm gonna compactify one of the dimension and discuss that this 3-dimensional limit. But anyway, before going that, let's discuss what this duality means. Okay, so let's check what's happening. If this, okay, in left-hand side is scalar theory, UN theory with NF scalar field. And if scalar field mass squared is much bigger than the gauge coupling to the force, this is a dimensionful parameter. So let's take gauge coupling to be 1 because it's dimensionful, it can just give you a unit. And if scalar field is much bigger than this unit 1, then what happens is that the scalar field, you can decouple the scalar field. And the low energy limit is, of course, just the UNK theory, right? And the level rank duality says this theory is the same as this theory, SUK minus N theory. So it's just the same mathematically too. Again, and if the mass square is negative and big, negative and big means that the absolute value is big and negative, then again, what you can do is that the Higgs mechanism happens, and you can just calculate the vacuum, correct vacuum, and integrate out the heavy degree of freedom. And what you get is that because of the Higgs mechanism, the gauge group is reduced like this. And we know that this is the same theory as this SUK with this level, different level. And that is also happening in the right-hand side. So that in the right-hand side, we have SUK with this level. And if fermions are heavy enough, you can integrate out fermions. And actually this diagram gives you a Chern-Simons term. So that if you integrate out fermion, you get the Chern-Simons shift of the Chern-Simons level, this one. And if fermion mass term is positive, actually in 3 dimensions, fermion, the sign of fermion mass matters. So if it's positive, it gives you a positive shift, and if negative, it gives you a negative shift. And if it's positive shift case coincide with this one, and negative shift case coincide with this one. So this is just mathematically true that in the limit where the mass is much bigger than the dynamical scale, 2 theories are the same, flows the same theory. So this is just a true statement, not conjecture. It's true statement. The conjecture is that okay, maybe there's a region where the scalar mass passes through the critical point. Then it's a non-trivial physics going on. And that non-trivial physics is equally described by the non-trivial physics of this fermion theory with critical mass. So that's the duality it is proposed. You have a transition from this theory to this theory to this theory. And the left-hand side, it is described by the Higgs mechanism. Right-hand side is described by some fermion dynamics. So that's the duality it is proposed. And both theories have, of course, the same global symmetry that is required by duality. And that is actually interesting. So right-hand side, you can see that the fermion theory, we have SU and global symmetry because we have n fermions. In three dimensions, there's no chiral symmetry, just one SU and F. And there's a baryon U1 symmetry, U1 baryon symmetry. So SU and F times U1, this is the global symmetry of right-hand side. So look at the left-hand side, you have SU and F symmetry because we have U and F scalars. But you can't find the U1 global symmetry, U1 baryon symmetry, right? Because U1 baryon is already gauged here. So there's no global symmetry. But actually the global symmetry appears from this U1 factor. So in 3 dimensions, you can make this kind of current. J mu current is contracting F mu nu with epsilon tensor. That gives you a current. And this is trivially conserved by Bianchi identity. So that this is conserved current. So this gives you a conserved symmetry. This gives a symmetry. So the left-hand side, we have SUNF times this symmetry, U1 topological symmetry. And the right-hand side is, SUNF times U1 baryon symmetry. So this is the way to find the same global symmetry in both sides. And what's interesting is that the charged object under this topological symmetry is a monopole in the left-hand side, because this is a magnetic charge. So it's a monopole. And the right-hand side, it's a baryon, because the U1 is a baryon number. So the monopole in the left-hand side is a baryon in the right-hand side. This is the correspondence in this duality. So it is somewhat interesting that in this theory, you have a monopole, and that monopole is corresponding to the baryon in the fermion theory. And that will be interesting if you go up to 4 dimension. Our baryon, proton, neutron, maybe a monopole in some dual theory. That's something interesting that I want to pursue. So let me explain a little bit more about the diagram I already showed before. So the Komárowski and Seiberg wrote this phase diagram, and this is the QCD3, QCD fermions, okay, NF fermions. And we have, in a very heavy mass limit with positive mass limit, we know that theory is this one. And negative mass and very negative limit, we have different topological fields, Chern-Simons theory. So this is known. And what they propose is in the middle, there's a nonlinear sigma model where the global symmetry UNF is broken down to this times this. So the massless pion appears. The symmetry breaking phase appears in the middle. And this is based on the duality consideration. Okay, so we know that this theory is the same as this theory. And this theory you can obtain from the bosonic theory, like this. And the one limit of the bosonic theory. And this theory exhibits symmetry breaking if the mass squared is negative, and where you get is the pions. And the same as this side. So that the whole picture is consistent with the duality that we discussed before. So this also passes the non-trivial tests like time reversal symmetry and so on. But anyway, so this is the conjecture picture of the QCD3 phase diagram. It's not very difficult, right? So heavy mass limit, CFT, and then TFT, topological field theory, and of course, this side was also topological field theory, and inside we have a non-trivial symmetry breaking happens. So that's the 3D picture. And I would say this is pretty similar to QCD4 in 4 dimensions, usual 4-dimensional theory. We know that in usual 4-dimensional theory, if quark is light enough, what happens is that the QQ bar condensation happens and the chiral symmetry is broken, and what we get is a nonlinear sigma model. So the theory is massless pion appears. So that sounds kind of familiar. So maybe it's similar to QCD. And if there's some dual picture like this U something theory, then that should be a hadron theory. Right. So the dual theory in 4 dimensions, there may be some dual theory as a theory of hadrons. So hadron Higgs mechanism may be describing the symmetry breaking phenomena like this in QCD, QQ bar condensation. So that will be fun. So the duality says that, okay, in the fermion side, we have gluon quarks, and also the N quarks forms the baryons. That's the usual story. And there may be some dual picture. The dual group is U and F, and the gauge bosons are hadrons, and the hadrons are dual to each other. Gluon and as I claim that the vector meson should be the gauge boson because of its group feature, and quarks may be a soliton made of this UNF theory, and baryon should be a monopole. And pancake story I'm gonna tell you later. So I mean, this gives you some new picture of the hadron world, so that would be fun to think about. Okay, so let's try to be more concrete. So we have some equations here now, but it's very simple. So what I'm going to talk about is S1 compactified QCD. So that means we have gluon kinetic term and theta term and quark kinetic term, that's it. But what we do is that the Z direction, X3 direction is compactified on S1. So if you go to one direction, you come back from the back. You know, that's some funny word. But anyway, so it's one compactified. And also I put theta angle to be no X3 dependent. So it's kind of axion background. And on top of that, I allow this theta angle to wind this direction. So if you integrate this theta can start from 0 and come back by 2 pi. And 0 and 2 pi is the same point because theta is an angle. So that you can have that kind of a background as a consistent background. And I mostly discussed the case with K to be NF. That means start with 0 and come back with 2 pi times NF. NF is a number of flavor, number of quark fields. That's it. So it's very simple. And winding theta means that, okay, if you start from x equal to 0, come back, okay, 2 pi times NF. And because 2 pi times integer is 0, the same as 0, so you can identify. So of course, this is consistent with this one compactification. So this funny background, I'm going to talk, discuss QCD on this non-trivial background. It's not totally our world. It could be our world if there's an axiom, but we need to compactify one of the dimension, like this. But anyway, so in this way, but we can get the low energy effective theory as a 3-dimensional theory, and we can get a hint from the 3-dimensional duality. Okay, let's continue. So that in a small radius limit, we can discuss. That means, okay, we have QCD in 4 dimensions, and we have a dynamical scale, QCD, lambda QCD. If radius is much smaller than lambda QCD, you can, at the compactification scale, the QCD is weakly coupled. So that means you can freely do the KK decomposition of just QCD quark field and gluon field and do the analysis. And also the large radius limit, if in compactification radius is much bigger than lambda QCD, then the correct language we use is the chiral Lagrangian. The low energy degree of freedom is just pions. So the large radius we have, theory of pion, and we can do the KK Kalsakline decomposition of that chiral Lagrange. So that should be the low energy limit of this in this region. So we are going to change the radius and discuss the change of physics. So first, let's discuss the small radius limit. Okay, and this is not very difficult. Just do the KK decomposition. One of the non-trivial part is the winding of theta. But as you know, the winding of theta you can actually eliminate by the chiral rotation of fermions. But instead, that gives you some non-trivial term in the fermion, and that appears in the KK decomposition like this. This ML and MR is some integers, but related to the parameter K, the winding of theta. But anyway, you can do just KK decomposition, just expand the 4-dimensional field with respect to the X3 and some eigenfunction there, psi n, and usual thing. But non-trivial thing is that this A3 field, the X3 direction of the gauge field becomes a scalar field now by the KK decompose. I mean, it's a dimensional compactification. And we have to discuss the vacuum expectation value of this A3 field, so-called holonomy. And this A3 field gets potential at the one loop level through the interaction with fermions. Here, through the interaction with fermions. So at that one loop level, we get the potential, and you can discuss what's the expectation value of A3. And for example, SU3 with 2 flavor case, potential for A3 is given like this. Well, let's ignore this nu. Well, nu is actually the boundary condition of the fermion. This is the periodic and anti-periodic. But anyway, let's look at the periodic one. You see that the minimum is here and here. this is one-dimensionalized by the taking the ansatz like xi. Okay, this is the traceless, so xi minus 2. But anyway, this is, we can do that, the general analysis, but anyway, to illustrate, we just take this ansatz and calculate what will be the expectation value, and you can get this one. So A3 gets an expectation value. So that means by putting a expectation value here, fermions gets mass. But what's surprising is that A3 is of course an adjoint representation of this SUN, QCD. So giving expectation value looks like it's breaking the gauge group, but it's not actually. Expectation value is non-zero, but actually gauge group is unbroken. That's because what matters is the Wilson loop along the X3 direction. If you exponentiate this one, what you get is 1. So actually the gauge group is unbroken with this expectation value. In this KK decomposed language, it's more simple. If you put this expectation value, you would get a zero mode to be a mass, to get a mass from this term, as usual Higgs mechanism. But that shift is happening to whole field, and actually still the zero mode remains from the other side, from some other location. So the spectrum still we have a massless gauge boson for whole SUN group. So that means the gauge group is unbroken, even if we have the wave in this case. So the SUN is unbroken in this theory, but fermion gets mass. Yeah, sure.
So with the boundary conditions, you mentioned boundary conditions, that was for the gauge field. Do you have any specific boundary conditions for the fermion?
Yeah, it's a periodic boundary condition.
It's all periodic and no flips of sign or anything like that. Or...
Yeah, because it's S1, it's not all before. So S1.
Yeah, no, okay.
Well, if there's another S1, you can get some twisted boundary condition. But it's just S1, so it's periodic boundary condition.
Okay, thanks.
But yeah, it's somewhat fun to see that there's no gauge symmetry breaking with this thing. And this is actually not true if you have some adjoint representation fermion and so on. It's a property of the potential generated from the fundamental representation of fermions. But anyway, SUN is unbroken, and fermions are all decoupled. And it doesn't matter what boundary condition you take for fermions, what you get is the same picture. SUN unbroken, and fermion gets a mass.
Ryuichiro, can I ask the question? I mean, this is an unusual thing I couldn't understand. So can you do some gauge transformation and gauge away this vacuum then? To make it zero or something?
You mean this A3?
Yeah.
So the gauge invariant stuff, well, maybe yes. This is gauge dependent. I mean, how do I see?
All right, maybe we can talk
gauge invariant thing is exponential IA3, integrated over the X3 direction. So that's the gauge invariant stuff.
Mm-hmm.
Wilson loop. And that doesn't get a wave.
Okay.
Yeah.
Yeah, thanks.
Yeah, so a little bit non-trivial. So it's called the Hosohtani mechanism and heavily used in the phenomenology. I mean, what is called extra dimension phenomenology. But anyway, okay, and what's also interesting that we have this ML and MR, and it shifts the left-handed and right-handed fermion in a different way, the mass of the fermion. And usually it doesn't matter what the mass is. But in 3 dimensions, as I said, the sign of the fermion is important. Fermion mass is important. And because of the difference of ML and MR, actually the Chern-Simons level is induced from that. You may remember that this diagram gives you a shift of the Chern-Simons level at low energy. and it depends on the mass of the fermion, the sign of the fermion mass. And the sign of the fermion mass shifts because of this this K parameter, the winding of the theta angle. So the low energy effective theory is actually a Chern-Simons theory. SUN level K is generated. And there are no fermion, no massless fermion. And we know what happens to this theory. It's a Chern-Simons series, it's gapped and topological. So that's it. So this is the low energy effect, low energy limit of the theory. And as we already see, this theory has a dual picture. It's exactly the same as UK theory with level -n. This is mathematically the same. So the low energy limit is this one. When the radius is small, if the radius is much smaller than the lambda QCD, what you get is this theory, gapped theory. So that's the usual picture. I mean, this is the picture I get. So let's talk about the large radius limit. As I said, that we can just compactify the chiral Lagrangian. That would be the large radius limit. But don't remember that. Don't forget that we have winding of theta term that you need to consider. So we can write down the effective Lagrangian like this, and I put eta meson here. The pion, usual pion and eta meson here. The U1 part. I call it eta or eta prime. It's the same thing for me, you know. Well, it's a different particle actually, but I call it sometimes eta and sometimes eta prime. It's sorry for the, I know, tropy convention. But anyway, this is the mass term for the eta prime. Eta. I mean, it looks complicated, but it's just this eta minus theta over NF to the square. Yeah, this is, so it's just the usual chiral Lagrangian, the lowest term. And we add the mass term for eta. So this is you know the well-known low energy effective theory of QCD. And because we have a winding of theta that needs to be care, so we have to solve the equation of motion for eta, where we have non-trivial term here. So this is just the, you know, kinetic, coming from kinetic term, and this is the mass term. So this is the, and you know, we have a background where the theta is winding, going starting from 0 and come back with 2 pi NF, right? That's the thing. So the solution of the equation of motion, the trivial one is the inside of this one is 0. And well, not quite trivial, but anyway, so that we can find a solution where this part doesn't wind. So that means eta gets winding. So the eta, if you, okay, the solution of equation of motion is that eta starting from 0 and coming back with 2 pi. That is gonna be the solution of the equation of motion. So we have to do the KK decomposition with that background. Okay. Okay. So, but anyway, as you may know, the eta prime potential is in this way, at least in large n limit, so that we have quadratic potential. So this is the combination of eta minus theta. But anyway, there's a quadratic potential, and at some point, there's a cusp. At some point, actually, at pi, there's a cusp. Well, this is not a good picture. This is only for one flavor. Sorry. So I mean, this is maybe wrong. Let's take one flavor. One flavor case at pi, we have a cusp. And at 2 pi, it come back to the same point. And 0 and 2 pi is the same point, because again, eta is, you know, introduced as an angle. So the 0 and 2 pi is the same point. So this is, at least in large n, it is known that we have a cusp at theta, eta prime equal to pi. So some non-trivial thing happens here. So that's the eta prime potential. But what I did is that this solution corresponds to just eta prime minus theta stays within one domain. I don't go beyond this one. So that's the solution. So that we are safely within the effective theory. Actually, later I'm gonna discuss what the case with this one jumps to here as you go around one dimension. But anyway, here I'm gonna discuss with the solution where the eta prime stays within one domain, so no magical thing happens. But that means if theta is winding, eta prime is also winding. Eta prime winding, right? Okay, and we know that there's a Bessemer-Witten term in 4 dimensions. This is completely fixed by anomaly, and the eta prime is coupling to the external field. So you can think of this as a baryon current. Baryon, okay, I should explain this. So this is the external gauge field. That means you can introduce weakly gauge the U1 baryon, right? If you weakly gauge the U1 baryon, you should get this term. I mean, in the real world actually happening, we are weakly gauging QED, right? That's why eta prime can decay into 2 photons. You know, so this is standard story, you know. Okay, pi on 2 photon, for example. So, you know, the standard story. So if you weakly gauge some of the global symmetry, what do you get is this Bessemer-Witten term. So this is completely fixed by anomaly. So we know this exists. And we know that this eta prime is winding. So that if you reduce to 3 dimensions, that means if you do the KK decomposition, we should expand with background where the d eta integration is 2 pi. So what you get is in the 3-dimensional theory, we get the Chern-Simons term, ADA term. But this is external field, not gluons. This is like photons or baryons, baryon.
What is the trace over there then? Is that if it's a abelian field?
No, sorry. So this is the whole SUN gauge and global symmetry, a UNF global symmetry. Okay. Here, yeah. So the there global symmetry is actually there are more global symmetry actually. SUN times SUNF, SNF times SNF. That's the global symmetry. But I just took the vector part. SUN plus R, SNF, L plus R part. So this contains baryon number. And also the vector current or the vector symmetry. But what most important part is baryon currents. Then you can the trace and just BDB, right? And BDB. So what you get is BDB in the low energy effective theory. And let's read off what's the baryon. What carries the baryon number? You can actually take a derivative with respect to B naught, right? That should give you a baryon charge. So that I already did that game, but okay, if you take derivative with respect to B, what you get is the magnetic field of B. So that means again, because this is going to a number, so the baryon number is carried by a monopole in this theory. So it's really the same picture as a 3-dimensional theory. So far, I haven't done any non-trivial things. It's just reduced the theory by Karuta-Klein decomposition, but you can see that baryon is a monopole. You can see in this 4-dimension, 4-dimension reduced to 3-dimension theory. But again, what I did is I'm working with some funny background where theta is winding. But anyway, in that world, baryon is a monopole. And so I could really see the similarity between 3-dimensional QCD and 4-dimensional QCD. Let's look at this side. So in 4-dimension QCD on S1 with some winding theta, small radius limit, we see that there's a topological field theory appears, gapped phase, SUN with level NF, that we get. And the large radius limit, of course, it's a theory of pions, but eta is winding. That means we have some Bessemer term that identify baryons as a monopole. And that is exactly the same picture as a 3-dimensional theory. 3-dimensional theory with large fermion mass limit is gapped, and small fermion mass limit gives you a nonlinear sigma model with Bessemer term, like this. This one. Some large radius, a large mass limit, it's a topological field theory, and small mass limit, it's a not limit. Small mass, we have a nonlinear sigma model with best new term. Okay, so it's actually the same. I'm going to skip all the detail, but we know that in this QCD picture, we have a dual theory. It's some dual bosonic theory with the gauge group UNF. So my picture, which I want to propose, is that this extends also into the 4 dimension. That means the same dual theory is describing the same this transition, small radius limit to large radius limit. As you know, small radius, you can see small radius limit is gap and large radius limit is nonlinear sigma model. So there must be some phase transition. You know, there's a no massless field here, massless field there, so there must be a phase transition. And the effective theory to describe that phase transition may be this one, because it's similar to the 3-dimensional, known 3-dimensional duality. So that's something I want to propose. And so what? You can ask, so what? But actually, it's interesting to me because actually there's such a picture already known in 4D QCD where the gauge bosons are rho and omega mesons. You can see that, okay, the gauge group is UNF. And we know that rho and omega meson is a vector mesons that can form a UNF gauge group. So this vector mesons may be a gauge field of this dual UNF theory. And of course, those are massive. That means UNF is in the Higgs phase, but this transition may be described as the Higgs mechanism that rho and omega mesons. So actually, this treating rho and omega mesons as gauge bosons are called hidden local symmetry, and those are actually pretty much success. For example, well, maybe I'm not going to discuss all the detail, but wow, I took too much time. Well, okay, so okay, let me explain. So the vector mesons as gauge bosons are very long history, and actually, yeah, there are many phenomenological success. Sorry, I already spent 1 hour. No. So can I give me 5 minutes more?
Yeah, that's okay.
Yeah, let's go ahead.
Yeah, sorry. So I haven't gone into my story yet. So sorry. Yeah. Or anyway. So okay. The story I want to present is this one. So the behavior of hadrons. So we know that at large radius, we know that large radius means our world. There are massless pions and rho and omega mesons and so on. There are many massive particles. Okay, so that's the QCD. And when the radius gets small and gets to the critical radius, I propose that this rho and omega meson and massless pion and other scalar mesons form a UNF gauge theory, but it's Chern-Simons theory. Maybe I didn't tell you that the important thing that the Chern-Simons theory gauge bosons are actually massive, even though gauge group is unbroken. So that's why it's a topological field theory, and it's actually almost trivial. Low energy, there's no degree of freedom, but still the Wilson loop and the linking number, the topological thing is some non-trivial things at low energy. So the rho and omega still it's massive, but can be a gauge theory. When chiral symmetry is restored, of course, pion disappears, and rho and omega meson stays as some massive field, and it becomes a UNF minus N theory. And this is, again, mathematically the same as the SE and NF theory. So this gives you a consistent picture of this phase transition. Large radius, small radius, we know what the theory is. And only from the hadron side, you can actually see the consistent picture. Rho and omega meson becomes a Chern-Simons theory, and that is actually a dual to the gluons. So some hadron, KEK hadron duality in a big sense is emerged in this. of course, this is just a proposal, but it may, I think this is kind of convincing. So the proposal of 4D Lagrangian is like this. So it's not very difficult. Again, this is Chern-Simons theory. I know it's a 4-dimensional theory, so it's not a Chern-Simons theory, but again, the eta winding gives you a Chern-Simons term. So the low and omega meson theory can be a Chern-Simons theory at low energy when small radius. And large radius, we know that eta and theta, eta minus theta, this combination is 0, so we don't get the Chern-Simons theory, but at small radius, it should get us. This is proposal of the 4-dimensional theory. And this similar Lagrangian was proposed by Karadzic this year. Okay, so this is the proposal. And very nice, very natural, I think, candidate of this further UV complete theory is the holographic QCD, where the rho and omega mesons are already gauge field. So I think this is a natural connection. So let me tell you one of the story about baryon equal to monopole, which is somewhat fancy. So as I said, the baryon should be interpreted as a monopole in the Hadron picture. And in the large radius where the baryon, large radius means, again, our world, just usual. The baryon is just a baryon, right? It's not monopole, it's baryon, it's baryon. But close to the critical radius, there must, the 3D effective theory says that it is identified as a vortex, the monopole vortex. And what's the 4D picture? And the natural thing to extend to 4D is the string, vortex string of rho and omega. And how rho and omega meson string gets a baryon number in 4D theory, that's the interesting question. And that is actually connected to the work by Komar-Godowski, so-called pancake. So that if eta prime has some non-trivial configuration, if 0 here and 2 pi here, and 2 pi is the same as 0, so it's the same. So if you go through the pancake, eta is gradually changing 0 to 2 pi, but if you go outside the pancake, eta stays at 0. So this kind of configuration you can think of, the pancake. And we know that actually on this kind of pancake, some Chern-Simons theory is induced, and there's a mode, edge mode, so edge mode, when carries a baryon number. So this is the work by Komar-Godowski. So this has something to do with our things. Let me skip this one. So the rho omega string actually can penetrate the pancake, and that can get the baryon number because of the winding of eta. As I said, winding of eta gives you a Chern-Simons term. So at the large radius, at the vacuum, there's no winding, but if there's a pancake, you can get a winding and you get it a baryon number. So in that way, just a baryon can become a string in a small radius limit, small radius case, so that we can get the sense of how monopole becomes a baryon in this picture. So I think I should stop here. This is something unfinished talk. So anyway, let me give you some duality picture I want to propose. Is that okay? In the gluon picture, we have quark, anti-quark, and the color string. So this is a meson, right? So this is the usual picture. And even we have the same picture in hadron because it's the same object. Maybe monopole, anti-monopole connected by rho omega flux is the same as this one. It's kind of funny, right? Because quark, anti-quark usually makes rho meson. That's the usual story. But no, actually hadron picture, rho and omega is the fundamental thing, and that makes this thing. So also the baryon is usually made of 3 quarks, and in the hadron picture, it's a soliton. It's like pancake. So that kind of a picture appears. So let me summarize. In QCD, there must be a phase transition between large and small radius of base 1. The large radius, our chiral Lagrangian, small radius, it's a Chern-Simons theory. There must be phase transition. And the Higgs mechanism of the vector meson can be the dual picture of this transition. That's the proposal. Rho and omega meson are gauge boson. That theory may describe that phase transition. And Victor meson, okay, this part I didn't explain, so I'll just skip. So anyway, I am hoping that this view of hadron may give some new qualitative picture to the hadron world. Thank you.
Thank you very much for interesting talk. So we have time for some questions. We already had some, but we still have time.
Yeah, sure. Yeah, I have time.
Yeah, Mikael, maybe we can close the session because people may want to leave and
okay, yeah, okay. We close the official part
and then continue discussion afterwards.
Yeah. Let's do that. We close the official part. We think, but and can stop the recording.